So what we're now looking at here is an overview of the dynamics section. And so the dynamics is basically the study of why, or what causes, the causes of, the objects to move in certain ways. So kinematics just describes them, dynamics looks at the sort of causes. So the key things that we probably need here are Newton's laws of motion. So Newton has 3 laws of motion. The first law is called the law of inertia. Now the law of inertia is quite clear and it's quite wordy, but it simply essentially states that an object with mass will continue moving at constant velocity, which also implies in a straight line, because changing direction means it will change velocity. It will move at constant velocity, or remain stationary. In other words, it is constant velocity that v equals 0, unless acted upon by an unbalanced external net force. So basically the law of inertia says, if you've got, mass, then basically nothing will happen. It will just always keep doing what it's doing, unless, of course, you've got a net force acting on the object, basically. That's his first law. Mm-hmm. His second law is quite wordy, but mathematically it's basically F equals ma. It says that the acceleration of an object is proportional to the net force on the object and inversely proportional to its mass. Mathematically it ends up basically being F equals ma. Mm-hmm. Newton's third law, often quoted as action equals reaction, but that's very easily misunderstood and not really a very good description. It's much better to describe as any force will have an equal and opposite force acting. It will have, perhaps better worded as, it will have a force of the same magnitude, in other words, equal in size, and acting in the opposite direction. This is really saying that whenever your objects interact, you're going to get, there's always 2 sides to every story. So it's a bit like a transaction, right? If a transaction was made, someone sold it and someone bought it, right? If you give something to someone, someone gave it away and someone received it. There's always a, you gave $5, someone received $5. Any transaction can be thought of, there's always an opposite side, right?
Yeah.
All right, so those are Newton's 3 laws. Then, of course, to apply these laws, we will need to consider forces. So the idea of force is that it's a push or a pull. And it's a vector. So everything we talked about earlier about, drawing your diagrams and so forth comes into play. So you'll need to identify the type of forces. The key types that you will be using in your questions are weight, which is W equals mg, where g is approximately 9.8 meters per second on Earth. And you assume that this goes downward. There is the normal force, which you will just have to sort of calculate. And it's always perpendicular to the surface. You also have friction, which is often ignored. So if you're told in the question that you've got a smooth surface or anything like that, then you assume it's frictionless. But if the question tells you to consider it, you will need to consider it. So the friction force is equal to mu times n, where mu is the coefficient of friction. Depending on if the object is moving relative to the surface or not, you would either use the static or dynamic coefficient, but ultimately it's still a coefficient. And this always opposes the velocity, if moving, or the applied force, the applied net force, if not moving yet. So your weight, normal, and friction force are really your key forces, but obviously there's any sort of other applied forces. And those would include things like, your driving power. So any sort of force from a bicycle or an engine, your lift, and so on. Tension from a string. And other forces include, for example, air resistance, drag, and so on. But which ones you apply basically depends on the question.
Mm-hmm.
Okay. Basically, whenever you're doing a question, basically make sure you read the question carefully. Identify all forces. And by that, I mean both their magnitude and direction. And then draw a free body diagram. So once you've drawn a free body diagram, then of course, you kind of will need to look at what the question wants. Are you trying to do it, acceleration left, right? Are you trying to do it up, down? You may need to resolve. This will be better covered if we do an actual question, but right now, basically, you may need to resolve 2D vectors into 1D vectors in the appropriate direction. And that could either be horizontal and vertical, or parallel and perpendicular to the surface. Those are the common situations. Once you've drawn your free body diagram, then basically use F equals ma to do calculations.
Okay.
So that's your dynamics free body diagram there. We do also introduce other concepts. So we also introduce the concept of, work. Work is very simple. Work is calculated as force times displacement, at least the perpendicular components. So sometimes you might think of this as F times D sine theta. And this basically represents energy. So in terms of energy related to your dynamics, you'll note that energy, which is represented by work, is split into a few different types. The key ones are kinetic energy, which is the energy of motion. And the formula is half mv squared. You've got gravitational potential energy, which is basically the energy due to the gravitational field, and you calculate it by mgh. You've got elastic potential energy, which is basically half kx squared, which is basically the energy from elastic materials like like springs and rubber bands kind of things. And basically, there is the concept of mechanical energy, which is kinetic energy plus GPE plus EPE.
Oh, so sometimes when the kinetic energy and the elastic potential energy goes to zero, like mechanical energy will just be the gravitational potential energy, right?
Yeah. So if you think of like something just not moving at the top of a cliff, like before you drop it, its kinetic energy is zero. Its gravitational, its EPE is zero because there's nothing elastic there. So all of the mechanical energy is just your GPE.
Oh, okay. Yep. Okay.
So this brings into our laws. So you've got a law of conservation of energy. So this is a very general law that applies to everything. But basically that says that energy cannot be created or destroyed, only transferred from one form to another. Well, you actually also have what's called the conservation of mechanical energy. So this applies to mechanical energy only. So basically, if you've got an object that experiences, no sort of changes, no work is done on the object, overall, if it's subject only to sort of conservative forces, like if it's falling under gravity and so forth, then basically we say that mechanical energy is constant. And this is one way that we can use to solve problems, as you might recall, with related to dynamics.
Okay. Wait, so it's like after, like, if an object is keep moving and when it reaches to a cliff it falls down, and then when it's falling, like the mechanical energy is constant, things like
If
that.
you ignore air resistance and friction, yes.
Okay, so that's how we usually calculate the gravitational energy and then kinetic.
It's one way to do it.
Yeah.
So it depends on, depending on the question, the way so those might be better suited to when we do actual questions, but right now we're just focusing on the theory. But yes, those things may be the easiest way, it might not be. It depends on the question. You might find kinematics is easier, but you might find energy is easier. But you might recall that we've done these questions in the past and I've shown you both ways, and at least for the ones we picked, you can see how both ways will give you the same answer, but often the mechanical energy way for those questions are easier. Great. So the next thing then, of course, is moving on to momentum. So you have another concept called momentum, which is given, oddly, the letter P, and it's defined as mass times velocity. And basically, this is kind of think of it like sort of moving power. So really, this is particularly useful for analyzing collisions and explosions. That's why we calculate it for the most part. Now, we have the term called impulse, which is defined as change in momentum, which is therefore mv minus mu, which you can rearrange to get m times v minus u, and it also can be proven to be m times a times t, which we've proven previously. It's also equal to, therefore, F times T. So impulse is force times time. So impulse is change in momentum, but it's force times time. People get this mixed up with work, which is force times distance. They don't mean the same thing. Okay. Now, apart from this, then we also have the fact that your momentum is m times v. Now, this is useful for collisions and explosions due to the law of conservation of momentum. Which states that the total momentum before a collision or explosion must equal the total momentum after. In other words, P initial must equal P after.
Mm-hmm.
Okay. And this is what we need to basically calculate your momentum. All right. And then after that, after this momentum, remember the final thing we really need to mention is that your collisions are split into two types, into what's called elastic and inelastic. So your collisions or explosions could either be elastic or inelastic. Now, for all collisions, momentum is conserved. But if it's an elastic collision, kinetic energy is conserved as well. But if it's inelastic collision, the kinetic energy is not conserved.
Mm-hmm.
And that's basically your review of dynamics.
Okay. Yep.
Great.